Static analysis is the examination of code without executing the program. It's used to identify potential errors, code quality issues, security vulnerabilities, and adherence to coding best practices. Abbas Sabra is a principal engineer at Sonar, which creates tools to help developers produce clean code. Abbas specializes in C++ static analysis and began his career in the financial industry where he identified inefficiencies within the C++ tooling ecosystem. He joins the show to talk about static analysis and static analysis tool development. This episode of Software Engineering Daily is hosted by Sean Falconer. Check the show notes for more information on Sean's work and where to find him.
Abbas, welcome to the show.
Thank you for having me.
Yeah, I'm excited for this. So you're a principal engineer at Sonar. You're working in C++ static analysis. So can we start off with maybe you could give some insight into your role, your responsibilities? Like what's sort of like a typical day look like?
Yeah, so as you said, I'm a principal engineer at Sonar. I work on static analysis. I started my career in finance. I found myself writing my own static analyzer on the side, so I decided to join Sonar to work on static analyzer. I work on a team that is focusing on different languages, C++, Python, Java, C#, and my specialty is C++. And we try to integrate those analyzers in three products, Sonar Cloud, Sonar Cube, and Sonar Lint. As a C++ developer, my typical day is divided into three areas. We have a group focusing on the language and its best practices. So this group, we think about what is new in the language, new standard, what are the best practices, how can we help user prevent typical bugs and code smell in their code. We try to reflect on our checks, try to write a description of why we are suggesting what we are suggesting in an educative way. And we also, in this, we call it bubble. In this bubble, we work on automatic fixes for C++. So how to generate code that would replace the previous code in a way that would make it better. Second part is about bug detection. So here it's more like static analysis technique to find typical bug like buffer overflow, memory leaks, null pointer dereference in just random code that you cannot assume anything about. And this is kind of the challenging part because there's many heuristics that you need to apply. And the third bubble would be on product integration, how to interact with different compilers, build system, products in a way that would make the static analysis accessible to the user.
Once you've reached sort of the level of like a principal engineer, how much of your time are you actually like hands-on keyboard coding versus being more of like serving as a leader and helping other people within the company that are maybe more junior with you implement the right things?
The percentage definitely decreased since I joined. When I joined, it was 90% coding. Now it's around 30 to 40%, depending on the subject, of course, because sometimes there is some subjects that require expertise and you need to be kind of on the keyboard trying to implement a new feature. And sometimes it's just leadership, making sure that we have the right objective and we have the right organization to reach our goal. But I would say it's 30 to 40% coding these days.
I want to talk about static analysis to start. So there's lots of ways that we've built as an industry to help with code quality, catch errors, catch bugs, and stuff like that. Like, for example, code reviews. Now it's standard practice that you're going to commit code through a PR or whatever mechanism that you're doing it. Someone on the engineering team or multiple people are going to review that code and hopefully catch some issues and also help make sure that it's like following whatever the best practices are. But what are some of the things that something like static analysis is going to catch that is very hard to catch during a code review?
Our vision of static analysis, because there's many different tools that apply static analysis, but our tool focus believes that static analysis should happen on pull request. So every pull request should be statically analyzed, and it's usually done before the human code review. So what static analysis can detect in this case is, we believe at least that static analysis, we believe at Sonar that static analysis can detect things that are hard to detect by a human review. Like let's say that you remove a call to a function in your pull request and then the function become unused. Usually on GitHub, on GitLab, the pull request review focus on the changed code. So it's hard to detect by the reviewer that the function become unused. Or if you have a null pointer dereference and the null pointer is initialized 20 steps in the call stack, the code reviewer will be hard to detect those kind of things. And in general, these kind of coding guidelines are easier to detect by tools than by a human reviewer. A typical example is that I get a lot on my pull request by static analysis is that this function should be const. I modify the code a little bit to remove the side effect from it, and then it becomes const, but it's as a coder, you don't focus on these things. By doing static analysis, code coverage, even dynamic analysis in pull request, the end will be that the code reviewer will focus mostly on the functional review rather than the technical review, because no tool will be able to detect that you have a functional inaccuracy in your code. But many tools can do better than you in detecting violation of your company guidelines.
Right. Yeah. And especially like something like, a function no longer being used might be hard to tell if you're focused essentially on the PR for code review, because it's going to be such a micro snippet of the larger overall code base. And you may not know that, okay, well, it's no longer used by these, hundreds of different locations or something like that. That's kind of a hard thing to catch by a person. But in terms of like understanding the context of program execution, like if we have these, especially, if I think about like a web application or something like that, and I have different backend services that are maybe deployed in different ways that call each other, like how does that, influence or be taken into account during static analysis in terms of the context with which that you're actually going to execute the code?
The entire context is available for the static analyzer because, the compiler is compiling your code usually in building this context. So a static analyzer can redo what the compiler does. And most of the static analyzer, the first step is to redo the steps that the compiler does. There's many techniques. One of them is symbolic execution or data flow analysis. Symbolic execution is what we usually use at Sonar, which basically means that we are building a control flow graph for the program and we are executing it statically. The same way that you expect a program to be executed dynamically, of course, with a lot of constraint because you don't know the input of the program statically. So you are kind of building heuristics on what the input can be and what kind of constraint we have on it. But at the end, in terms of control flow and interaction with the different part of the code base, the static analyzer usually can do the same way that the program does when it runs.
So in terms of the control flow building, essentially is it like a call graph essentially that you're building up statically that represent what the flow of the program is?
Yes. So usually static analyzers start by parsing the code and you build an abstract syntax tree. And so from the AST, you build some sort of a control flow graph that represent how the program is going to run. And then you follow the control flow graph and you build information at each step of the program.
Yeah. So in some ways, it's similar to building essentially like a compiler, at least the first part. Then in terms of, when you're walking that graph, that's how you catch things like a null pointer or, basically an unused function, because in the unused function perspective, you'd have essentially a node in the graph that is not connected to anything. Is that right?
What you said is exactly right, because actually a compiler is a static analyzer, and usually when it compiles, try to detect that code and try to remove them, optimize them from your binary. We try to detect that store, and usually it warns about them. But if you're following the call graph example, and you reach a point where, for example, you know that X cannot be bigger than 5, and you have an if condition that say if X bigger than 5, you easily can detect that, well, this condition is always true by following the possible value of data on each point of the program.
Is building a static analysis tool for C++ more difficult, you think, than other languages?
It has its own difficulties. It's definitely more difficult than Python, for example, because Python has you can fit the grammar of Python in one page, but the grammar of C++ is multiple pages of complex grammar where each brace or parentheses in different location mean different things. One of the difficulty is parser. Parser in C++ is complicated and costly because the parser is as fast as the compiler usually, and C++ compiler are known to be slower than other languages compilers. Other challenge is that we have many compilers and each compiler has its own extension of the language. So if you are building a static analyzer, you need to think about each extension. Other difficulties like we don't have a common build system for C++ or dependency manager, so you cannot rely on standard structure of a repo. compared to Java, where you always have Maven or Gradle in your repository, or C# where you rely on NuGet. But these are the top 3 difficulties that usually come to my mind when I talk about C++.
Yeah, in terms of the compilation time, like how do you deal with the slow compilation, especially for large programs?
One technique is to use something called PCH, which is pre-compiled header. So if you are analyzing a pull request, you can pre-compile the code, and once you have a pull request, you only have to update the compilation unit that changed, and you don't have to recompile everything.
And then what about navigating the different types of compilers? Like there's not necessarily, depending on the system that you're, it's tied to the CPU, it's tied to the operating system. Do you end up having to basically run under different constraints?
The CPU part is not really relevant to static analysis, depending on the technique, because if you run the static analyzer on control flow graph, not on binary level, you don't have to care about what platform it is targeting, because on a higher level language like LLVM intermediate language or on an abstract syntax tree, the targeted architecture is less relevant. Of course, it matters sometimes, so you need to understand it. For example, on different architecture, you have different size of types, and if you store something that cannot fit on this type in this architecture, the static analyzer should warn. But you don't have to think about things on a binary level when you are doing static analysis.
What are some of the heuristics that you commonly use in order to figure out, for example, like if there's a memory leak within the program?
So memory leak is a hard problem.
Yes.
There is, especially in C++. We use symbolic execution. So basically, this control flow graph, we try to execute it statically and building symbolic value for each variable. For memory leak, basically, you need to detect a path where the memory is initialized and is not initialized. If you find this path, it means that you have a memory leak. And the common pattern is an early return or throwing an exception that avoid delete or the release of the memory at the end of the function. Symbolic execution cannot detect all these issues, because if you want to run the program statically, it might take as long as running the program dynamically, even more. So you need to put some bounds on the symbolic execution to be able to finish in a acceptable time, because remember, we said we need to analyze the code on pull request. Heuristic, in this sense, you usually try to limit the step of symbolic execution, try to assume a specific pattern in the code. In C++, there is kind of contract with assert. You can assert that this cannot be null, and you can detect those constructs and feed them to your symbolic execution to help it better understanding to the code. But at the end, you are trying to build heuristics, unlikely passes, to be able to simulate the program up to 80%. And we try to rely more on preventive measure. Like, yes, we can detect maybe 60-70% of memory leaks that are just in random C or C++ program, but it is much more efficient to help people use a newer construct that would avoid memory leak than to detect a memory leak. For example, using smart pointers or before smart pointer in C++ 98, there was this rule of 3 where you try to define a constructor, a copy constructor, and a destructor in a standard way that would be hard to lead to a memory leak. So this kind of general advice would avoid memory leak and would have basically no false positive, because you are not simulating passes in the code, no false negative, and would have more efficacy than symbolic execution. So we try to combine both of them to get a high coverage, but at the end, detecting 80% of the bug is already good, and you don't aim for 100% in static analysis, and you combine it with other tools like dynamic analysis and code coverage to reach this 99% safety or confident in your code.
You mentioned false positives, false negatives. Like, what are some of the situations where you might end up with a false positive or false negative?
Just to make it clear, false positive, and when the static analyzer report an issue that is not accurate. So it's if you say there's a memory leak while there's not a memory leak, that's a false positive. And false negative is when the static analyzer don't say anything while there's a memory leak. False positive, depending on the rule, sometimes it's enough to, for example, if you build a checker that say use a smart pointer, it's highly likely that you will not face any false positive and false negative, because it's not really depending on the execution path of the program. You are just trying to find instances where the user is using a row pointer, like a new, and tell them to replace it. And here you rely on standard method for making sure that your static analyzer is robust, like unit testing and regression testing. We do this kind of stuff to ensure that we don't have false positive and false negative. For symbolic execution, where it's path sensitive, it's more of a challenge because you cannot guarantee that, and you are basically running on any sort of code. And you do it by making basically the control graph very abstract in a way that it's not very affected by how the code is written. So if you kind of run the analysis on an abstract language where there's not a lot of room for getting it wrong, you reduce the possibility of false positive, because usually in C++, for example, you can initialize a variable in 10 ways. If the newer standard add another way, your static analyzer will be broken because it doesn't think about this way, and it will lead to false positives. But if you try to abstract all this way of initialization to a standard syntax that you run on the static analyzer, it's much more unlikely that you are going to hit some false positives.
What's the typical acceptable runtime when you're doing static analysis? So I'm doing a pull request. The static analysis is going to run. What kind of runtime am I looking at in order to get a report back?
If it makes your pipeline slower, you will highly likely not use it. And if you run your static analyzer on your main branch, it's not the right place to run it. So you need to run it in a way that is as fast or as slow as your build, for example. So usually if your project built in 5 minutes, the static analyzer should finish in 5 minutes. If you have a bigger project and your build take 10 minutes, also it's acceptable to run in 10 minutes because you need to analyze much larger code base. Mm-hmm. But as long as we keep this kind of ratio between build time and analysis time, it is generally acceptable, and you have to wait for your build anyway, so you can run the static analyzer in parallel and it will not slow you down.
One other thing in terms of the types of issues you might catch is, am I able to use a static analyzer to also catch things like concurrency issues, race conditions, deadlocks, stuff like that?
This issue is also similar to the memory leak problem because there is preventive measures. We have in C++ CPP core guidelines that try to give you some preventive measure for deadlock and race condition and things like that, like don't use a global variable, don't share variable between the threads, use a memory safe data structure. All of these things that would avoid the memory leak. It would avoid the race condition. And then you have trying to simulate the execution of a thread to try to detect race condition and deadlocks. And that would be the same way as memory leak. For example, if while you are simulating a thread, you find that the thread is locking the same mutex multiple times, that's already a deadlock because you cannot lock it while you already locked it before. So this kind of picture of best practices trying to avoid the memory leak, the race condition, and then statically executing your program to detect this race condition is the general pattern that we use for almost all bugs in the code, like memory leak and buffer overflow and race condition and deadlocks.
What about things like, if there's an infinite loop in the program, what ends up happening to the call flow graph that you're building?
So loops is one of the hardest problems in symbolic execution because sometimes it's not known statically how many times this loop can execute. And usually most symbolic execution have pattern to unroll the loop or to execute it on specific interesting value. But detecting infinite loop is one of the checks that a symbolic execution can detect. For example, if you are calling the same method without a condition, the engine can detect this infinite loop and report it to the user and stop the simulation of the engine because it knows that on this path there is a possible infinite loop.
Are there new advancements in this area that is particularly related to C++ that you're excited about, that you're looking at as something to implement into the work that you're doing at Sonar?
In static analysis in general, there's always new technique in symbolic execution or even new technology to run a static analyzer, like recently including machine learning in the past that a symbolic execution can take is beneficial. There's other languages where static analysis try to prove 100% that a method is doing what it's supposed to do. There's languages that are built around this, like Daphne by Microsoft. Usually you define the precondition and postcondition, and the static analyzer can build a mathematical expression that say, can I make sure that the output of the function, if the input is verified, that the output of the function will be as expected. But this technology cannot really apply to normal C++ code. In C++, I'm excited about a new feature that we recently worked on at Sonar called autoconfig, which is trying to make C++ analysis accessible to any type of project, independent of the compiler and toolchain that the project is using. And this is mostly useful because a lot of companies are stuck with older compiler and that don't have many toolings. And here in such technologies, the focus is it's mainly new parsing technology that focus on being able to understand when the static analyzer don't fully get the entire context of the code and try to build heuristics to understand it, even though it's not the real compiler that the user is using. And for this, we had to build a new part of the parser that can reason about code that is not typically understood by the top 3 compiler, Clang, GCC, and MSVC. And also, we have to detect dependency without relying on a dependency manager. So we had to rebuild our own dependency manager that would look at the user code, and instead of looking at the dependency manager, look at the user code and deduce the dependency. So we flip this around to know what kind of dependencies this code base is using. The end result of this is on SonarQube, now the user can just click a button and analyze their code without providing a lot of context, without providing actually any context about their code base. We detect everything automatically.
Where does a lot of this like innovation space come from? Is it driven by researchers in the space, and then you got to kind of stay up to date on like what the most recent stuff that's happening in the research world, or is a lot of it driven by industry, or maybe it's both?
It's mostly in research. Static analysis is a very researchy subject. At university, I did a project on formal verification, which is a form of static analysis to verify the program. There's always new papers that are about new technology in symbolic execution, taint analysis, data flow, abstract interpretation. So it's mostly driven by the academic world. Also, there is sometimes some non-standard static analysis contribution, like from machine learning and AI, that can be integrated into static analyzer to make it more powerful in terms of heuristics.
So do you spend some of your time looking at the latest research in order to figure out like maybe what's next or some opportunities that you can use at Sonar?
I personally don't have the time to do so. We have an R&D department that is mostly compiler engineers or static analysis engineers that have a PhD in static analysis that focus on this kind of what is a new top technology, reading some new paper to improve our product.
Okay, great. So I wanted to also talk a little bit about C++. You have a long history with C++ going back to the 90s. I also, I think that was around the late 90s was when I first started dabbling with C++, but I've never spent, the bulk of my career working in it. I've kind of like gone in and out with C++ at different points. And it's been around since the mid 80s. There's been a lot of change in that time. I remember being introduced to STL, the standard template library, which was a huge leap forward, I thought, at the time in terms of having built-in data structures and algorithms at your fingertips. So what are some of the major milestones in the history of C++ and its modernization?
Yeah, before going into the detail, how was your experience with C++? It might help.
I mean, I feel like I have a love-hate relationship. So I did competitive programming in university, the ACM ICPC programming competitions. And the only languages available at that time were C, C++, and Java. And I did all of my coding in C++. The only real industry experience I had was during my time at Google, where I wrote, I think this might actually still be in use now, but I wrote a program there to help add additional security essentially to the way that text messages get sent. And that was probably, I think every text message at Google for a period of time was going through that program. So that's like my most successful in prod thing that I've ever done in C++. But that was the most sort of more recent experience I had where I started to actually touch into some of the more modern points of it, like smart pointers and stuff like that.
Makes sense. I mean, most of the C++ developers that I met have love-hate relationship with C++, and that's for a reason. So C++ was started in the 98 standard, which was trying to do C with classes, so trying to give you some level of abstraction on top of C. And the main motivation was, well, you can migrate easily from C. You get classes and you get inheritance and all of the object-oriented features without paying extra cost for performance. So there's always this promise of zero cost abstraction in C++. And C++ 98 was at the time a good, I mean, it's definitely good progress from C. It's hard to imagine yourself writing a large program with C, even though Linux is written in C, but I personally find it hard to reason about a large program in C. With time, there was a lot of introduction of new languages like Java and C# and even more modern language like Kotlin and Go. And C++ needed to keep up. And for a long time, there was some minor improvement in C++ or 3, but it didn't provide anything new until C++ 11, which was like a totally new language, basically. We got move semantic, we got smart pointer, we finally get multi-threading in the language, which was a big thing. We have implicit type detection. You can write auto instead of var in Java to not spell the type explicitly. So it was like almost a new language. Even it's a new language. Like if you write now in C++ 11 and you use only C++ 11 features, you cannot recognize that it is C++. Even one of the most impactful features that it's still heavily used right now is lambda expression, which is also available in many other languages. So C++ came and made the language much easier to use, especially smart pointer and all the memory issues. Then after that, the language started to pick up speed. They started to release a new version every 3 years. We got C++ 14, which was a small standard compared to C++ 11, and that was a good decision to, it's not good to put a lot of feature in C++ 11 and get a lot of new feature in C++ 14. So it was mostly perfecting the features that was introduced in C++ 11. Then we get C++ 17, which was, I would say, a utility version, because we get things like optional, stud variant, stud any, string view. We got a file system. So we got a lot of the good stuff that you would use in a normal program that you could do before, but now you can express it in a much easier way and safer way. For example, for a stud variant, previously you have to use a union and keep track of what element in the union is active. Now you can use stud variant and it's much easier to use. So C++ 17 was focusing on this utility improvement. And then you get C++ 20, which is almost like C++ 11 in terms of number of features. We get coroutines, which are also a language feature that's now available in many languages. We get models. Models is a new way of building your program without relying on the old header file and preprocessor way. So this thing should make the compilation faster. That's its promise, and should make static analyzer faster. Also in C++ 20, we got ranges, so kind of patterns like map, filter, reduce is now very easy to write in C++ 20. So C++ 20 is a very large standard. And now we have C++ 23, which is, we go back, it's like now we have a standard that just go over the previous standard and fix normal small things just to give it time before introducing the next big thing. So C++ 23 is similar to C++ 14. It's just a small standard with a lot of small utility.
When was 11 introduced, and what was the motivation to modernizing it? Was it essentially to try to keep C++ relevant?
Trying to keep it relevant, yes. And I mean, every language is evolving, and looking at C++ not evolving since 10 years, it was difficult to still advocate for the language, even though the use cases of C++ wasn't challenged. In C++ 11, there was no language that is kind of competing with C++. There's no language that has the abstraction without the performance cost. So it wasn't out of competition, but it was out of, I mean, the good thing about C++ is that it's run by an ISO committee and many people can contribute, and they decided to improve the language, and that was a big favor for the C++ committee, for the C++ community. Sorry.
I mean, what about in terms of competition now with like newer languages like Rust and Zig? Are those starting to take people away from C++, or are they not directly competitive?
Zig is not directly competitive. Zig is more competing with C. It doesn't have a lot of abstraction. So Rust is challenging C++, but I don't believe it is yet there. So if you look at Rust objectively, and in my subjective view, Rust is a better language than C++ in terms of getting things done as fast as possible, because you get dependency manager, which is really hard to do in C++. You get a lot of utility, better standard library, and all of these things. But when you make a decision about a language, usually you take many consideration into account. You take how many C++ developer you have in the industry and how many Rust developer you have in the industry. You also do some risk management and you say, is it guaranteed that Rust will be there in 5 years? Because C++ is definitely going to be there. And Rust, it's a real challenger, so it's not like Zig or the other languages that are still early, but only time can tell if it's going to be a real competition. Usually, most languages that try to compete, the killer feature usually is being interoperable with the previous language. So C++ was with C. Kotlin is succeeded because it was easy to combine it with Java. TypeScript with JavaScript, same pattern. So unless Rust do some heavy investment to make it really easy for a code base that is written in C++ to migrate to Rust, or to at least start writing code in Rust without doing a big investment. If they can do that, it will be definitely successful. But that's basically the challenge, because it's not only about how beautiful the language is. There's a lot of things that you have to take into consideration. And recently, there's many languages that were introduced. We have Carbon, which was introduced by Google to compete with C++. Many people that work on it are actually part of the C++ committee. Also, we don't know if it's going to succeed or not. And we have CPP Front, which is trying to build on top of C++ by keeping the good subset of it. And say, for example, you can write this new subset, the good subset of C++, and use it with your old C++ without need to learn about all the uncommon feature, or let's say not very relevant features that are still in the language but don't have many use cases. But Carbon in CPP Front is still in the early days. Rust is the biggest competitor of C++.
When the modernization started to happen, what was the reaction from sort of the base that had spent the bulk of their career programming in C++? Was this met with positivity, that they were happy that these things were being introduced? Or was it more resistance of like, hey, I've been doing it this way for 20 years. Why are you now introducing these new constructs that take away from what C++ is supposed to be?
I think it was mostly positive, at least in my community, the people that I interacted with. And this boiled down to one thing, that if the language adds smart pointer, for example, you don't have to use them, but they are just an extra tool in your toolbox, basically. There is some features that get a bit of pushback, but most of them are positively received. I think most people complain about the things that are not yet in C++ than the things that were introduced to C++. Yeah. If you talk to a C++ developer, they will complain why we don't have reflection yet, or pattern matching, or even networking libraries that is part of the standard library. So the usual reaction of a C++ developer is, can I have more, rather than why are you introducing all of this?
And then you also mentioned some features of the language that are mostly sort of obsolete, but they're still there, probably for backwards compatibility reasons. And there's like a lot of, I think, things that were introduced to C++, like little intricacies that don't necessarily exist in other languages. Like things like operator overloading, multiple inheritance aren't super common in other languages. I understand why they're there, and I've used them, but they lead to some challenges as well. But what about like virtual inheritance? Like, can you explain virtual inheritance, and have you ever actually used that?
Yeah, let's introduce it by saying there's a lot of features that are there for backward compatibility. Like C++ 11 introduced type aliases, but C++ kept the C way of introducing type alias, which is a type def. So we don't remove those because of backward compatibility. Things that are broken in the language that are introduced in C++ usually get removed, like auto pointer was a smart pointer that was part of C++ 98 and got removed, and C++ removed dynamic exception specifier from the language. So they try to remove things when it's introduced by C++. They don't try to remove things that even if it's no longer relevant, break backward compatibility with C. Now, there's a lot of features that exist in C++ due to its original design. Originally, C++ have multiple inheritance, and it's a tool. You should use it carefully, but it's useful in some places. And when you have multiple inheritance, you can get a shape which is a diamond shape. Let's say you have a base class A, you have B and C that inherit from A, and you have D that inherit from B and C. So you have a diamond shape inheritance. When you have this pattern, D is basically inheriting A twice. You don't have this problem with other languages because there's no multiple inheritance. And once you have A twice, you have all sort of problem like ambiguity, because which A are you referring to? The one that comes from B or the one comes from C? And to solve this problem, we have something called virtual inheritance to say, yeah, even though I'm getting A twice, I only want it once. Why is it useful? I mean, if you are starting to write a code from scratch, I never used virtual inheritance, so it's one of the features that I would argue that you can, in case of a diamond shape, you can raise a compiler error and not accept this feature overall. But it was there from the beginning, so it's removing it would break users that rely on this feature. And there are use cases for this feature that you can argue they are not good use cases, but there are use cases for this feature. Like if there's code that you cannot modify that throw an exception, if you want your new exception to be able to be caught by the two handlers, you have to add a new derived class that would inherit from the two exception class. So I'm sure this example wasn't very clear, but there is cases in your code while coding where you have a lot of constraint. You cannot change this code. This code comes from a library, and virtual inheritance can be a workaround in your toolbox that you should probably not use, but you can use.
What about like friend functions? I don't think that's something that you typically see in other languages either.
Yeah, friend function is still something that you don't typically see, but friend function is more useful than virtual inheritance. Friend function is also part of the design of the language, because if you look at Java and C#, they all have this hierarchy where you have a base object that every class inherits from, that define things like how to print the object, how to hash the object, and things like that. In C++, we don't have this, which is good for performance. That's the reason why you don't have a common base class. And other languages has something also called package private or package visibility. So you have private,
Right, yeah.
public, protected, and package private, I call it. And C++ don't have this, and friend would usually solve this problem. So let's say you have a factory pattern, for example. In Java, I would put the constructor as a package private, and I would create a factory class that would call the constructor, and you can only call the constructor from this package or from the unit test, for example, of this package. In C++, you can either call it private, and then you cannot instantiate the class from outside, or you do it public, then the user might misuse your interface and don't avoid using the factory pattern. Then you would solve this problem by calling the factory class as a friend, and then only the friend can access this constructor. Another case is operator overloading. So usually operators are declared as a friend, then defined as a free function to access the internal field. And for example, how to print a class in C++, it's commonly implemented as a operator less than, which is a friend function to the class that have access to its internal field. While in Java, you would implement it as toString method that inherit from the base class object. So friend is like a unusual design, but if used carefully, it's not really something bad per se.
Yeah, absolutely. And then are there other features like things like, CCast or virtual inheritance that are basically obsolete in some fashion from people who are writing new code in C++, but are still technically available?
Yes. If we go back to the hate-love relationship, is that even if you learn modern C++, you have to still understand all the C construct. You still have to understand how function pointer works. You still have to understand Ccast, which I would argue that there's no use case for if you are using the C++ explicit cast, like static cast, dynamic cast, reinterpret cast, const cast. All of these things replaced CCast, but it's still there because of backward compatibility. And as a C++ developer, I don't love the fact that I still have to remember how all of these things work, even though I never use them, because some other colleagues might use them, or you have an older code base and you still need to understand them. So in general, there is in C++, and objectively C++ is a bloated language. There's many things that you need to understand, but you should never use. And CCast is one of them. We talked about virtual inheritance as another one. There's 10 ways of initializing a variable in C++. You don't have to remember how each one works if you use always the same way. Using type alias and type def, you should use type alias and never use a type def, no more at least. And
what about define versus constants? Sort of the way of defining a constant in C is supported in C++, but there's also, you can define something as a constant.
Yes, so C++ has a C preprocessor, so you can use define, and it's never a good idea to use define. The use case for define is that depending on the compiler might define different variable depending on the architecture or target architecture that you are building to. That's in terms of use cases for the define. But as a software engineer writing your code that is typical C++, you don't need to use the preprocessor. Usually the recommendation is if you can avoid the preprocessor, you should avoid the preprocessor. So in C++ 98, in most cases, you should write a const variable instead of a define, unless the use case for it if it's platform-dependent macro. So it's not really a variable. It's a variable that is defined differently by the compiler depending on your platform. We still have a lot of old code bases that use define, but that's something that should be refactored. Even in C++ 11, we have const expr, so it's a compile time variable, and it is used now for the global const variables.
So we've been talking a lot about some of the modernization that's happening in C++. So what's kind of next when you look ahead in the landscape of C++?
So there's two parts. There's what is next in terms of compiler support, because there's features that were standardized that not every compiler implement yet. Like models is part of C++ 20, but it's not really yet fully supported by all the compilers. It's supported by MS3C. Clang is on the way, but people are looking forward to use this feature. And that's a reminder for the committee not to when they define things, it doesn't mean that it's going to happen directly after compiler need times to implement this language feature. But as a language feature, most people are looking at things like reflection. Reflection is something that exists in every language that we don't have. Contract. Contract is a feature that we hope to get in C++ 11, but we didn't get it yet. Contract is a way of saying that this function, these are the contract of the function. For example, if you have a variable, you can say that I expect the input of this function to be always positive. And if it's not positive, the contract is broken. And for example, abort is called or something similar to this. And contracts are very useful because even they help static analyzers. So if a static analyzer can see the contract of every function, it can help it optimize the way it is simulating the program. So reflection, contract, pattern matching. Now we have in Python pattern matching, but we still don't have it in C++. In terms of library, networking is a common thing that you would need a separate library to use in C++, but it would be great if we have it in the language standard.
If networking was built in as a standard, do you think that more people would be building like the back end of web applications in C++, similar to how like Go has become a very popular language for building web backends?
Not necessarily. I don't think if you add networking, C++ will be popular in networking. It's mostly if you have a small networking tasks that you want to do and you are already using C++, you don't have to introduce another language or another library to use it. Also, if you are in university and you are learning about networking and you are already familiar with C++, you don't have to learn another language to get introduced to networking. But for C++ to be competing with Go and other languages in networking, it would need much more than a new library.
Yeah. Well, Abbas, thank you so much for being here. This was really interesting. I think there was a lot of stuff that we covered on the static analysis front, as well as a lot of the history with C++ and all the fun intricacies of the language.
Thank you for having me. It was a pleasure.
All right. Cheers.